cargo plane is flying 90 meters per second horizontally when it drops the relief supplies with the intent of landing on a remote island. So what's given to us here is this 90 meters per second horizontally. This is the actual V0, or the plane's speed, okay? And that is basically the same speed as your package. So even though the package is dropped, it is still traveling with the airplane horizontally at 90 meters per second. Okay, so here, if the plane is flying at altitude of 120 meters, so our y initial happens to be 120 meters, and of course my y final is equal to 0 meters. Okay, how far in advance of the island should the plane be when cargo is released from the plane? So this distance that cargo has to travel horizontally, that is your range delta x. Okay, and that's the ultimate goal, to find out when it should be dropped. Well, if we know the height, we can calculate how long this package is going to stay in the air before it hits the ground, right? So once we find that time, we can actually find this distance, because we know the horizontal velocity of that package. Okay, so just to visualize it, here's my package that's released from the plane. This package actually will have horizontal velocity Vix, and this Vix is the exact same velocity as the V0 of the plane, which happens to be 90 meters per second. Okay, so we also know the initial velocity in y, VIY, is 0 meters per second, because it is just released from the airplane that is flying horizontally. Okay, so this will fall and hit the ground. Okay, and this is the delta x that we need to calculate. Okay, so first step is to find time, I think, right? First step is to find time. If you can't really do anything or start anywhere, I would start with finding time. Okay, so here we could say my y final is equal to 0 meters. My y initial happens to be 120 meters. My VIY is 0 meters per second, because it is just released as it's flying horizontally. And my A sub y is equal to negative 9.8 meters per second squared. What I'm looking for is the T total for how much the package is going to stay in the air. It looks like equation number 2 will work out very nicely. So here, my y final is equal to y initial plus VIY T total plus 1/2 A sub y times T total squared. So if you plug in the values, you got y final 0, y initial 120, plus the whole term drops out to 0 because the initial velocity in y is 0, plus 1/2 times negative 9.8 times T total squared. So if you clean this up, my 0 is equal to then 120 minus 4.9 T total squared. So T total is equal to simply square root of, right, 120 over 4.9, which comes out to 4.95 seconds. Okay, so the package will be in the air for 4.95 seconds. Well, if that's true, it's going to have to travel horizontally for 4.95 seconds. Okay? So it will travel this much distance during that time because it's flying with the VIX of 90 meters per second. Therefore, my delta x is equal to then 90 times 4.95 seconds. So my delta x comes out to 445.5 meters. This is the correct answer. Okay. All right, any questions? All right. So, if you drop it at this time, that's what happens. All right, let's take a look at the next page. If you take a look at the next page, it looks like we have a launcher here, right? So the cart is moving at 0.5 meters per second to the right at time t is equal to 0. The ball is shot straight upwards with speed of 25 meters per second. How far to the right does the cart move when the ball lands back into the cup? Well, before I solve this, I want to show you a little demonstration. All right. So if we were to look at this, the ball, even though it's shot up, it also has horizontal velocity that is exactly same as the cart. Okay, so initial position of the ball right here, right? The initial position of the ball, y initial, happens to be 0 meters, but the final position here is also 0 meters. Okay, for the ball, and the initial velocity for the VIY of the ball, which is this right here, happens to be 25 meters per second. Okay? And the initial velocity for the cart here, VIX, is 0.5 meters per second. So this is like the projectile motion for the cart, right? So again, first thing to do is find time. Okay, I mean that's probably the best thing to do. Find time. Okay. Then let's write down everything we know for to find time in the y direction. So my y final is equal to 0. My y initial is also equal to 0, right? My VIY is equal to 25 meters per second, right? My a sub y is equal to negative 9.8 meters per second squared. Let's look for time that ball stays up in the air. Okay, let's see how much time it takes for ball to go up and come back down. Again, this looks like a nice second equation problem. This is the total time, by the way. Okay. Therefore, when I plug in the values, I get 0 is equal to 0 plus 25t total plus 1/2 times negative 9.8 times t total squared. So if I clean this up and factor out a t total from both of these terms, right, what I have left is 25 minus 4.9 t total as my equation. So to satisfy this equation, 0 has to equal to all this mess. But if my t total is 0, then it satisfies whatever this is. It doesn't matter. When you multiply by 0, you get 0. Or you could set this parentheses equal to 0, and when you set this parentheses equal to 0 and solve for time, it doesn't matter what this is, it'll be a 0. So my t total is equal to simply 0 seconds, or, right, 5.1 seconds. Okay, that's 25 over 4.9. Okay, so most likely I would use this. Okay, then let's calculate how much distance it travels horizontally, right? So my delta x is equal to VIX times t total in this case. So my delta x is equal to 0.5 meters per second times 5.1 seconds. So the ball will be caught at 2.55 meters to the right. Would the time change if I make the car go faster? What would change if I make the car go faster? Instead of half a meter per second, let's say I make it go 2 meters per second.
Oh, yeah.
Will it make the time change? No, because it is completely independent of the vertical motion. Because it's still going to be shot at 25 meters per second. So what's the change? What's the difference? Which distance? Horizontal. Yeah, it will travel a lot further horizontally before it catches the ball, basically. But the time will stays the same. Okay, because it is independent of horizontal motion. Does that make sense? Okay. All right. Any questions? All right, I'll stop there. And then, as I promised.